John, for inviting me. We were locked down a long time in Seattle, and, I don't know, a lot of people talked about when the lockdowns ended that they had this huge sense of relief when they went back to church, and they had this sense of fellowship. And I'm not actually religious, but to me, giving talks with my colleagues, this is my fellowship, and so it means a lot to me to be here, especially, and starting off in Cambridge is really exciting. But as I talk about being grateful for academic fellowship and the way we share ideas, I did actually have doubts whether I could come today. And that's because over the last 2 or 3 years, I've actually avoided giving talks where administrators aren't fully supportive of free speech. Free speech is core to what we do and is very important to me. I think there's a distinction between college administrators and departmental administrators, and to be honest, canceling it John at the last minute, and I'm springing this on John, which is also terrifying, was a terrifying thought. Really, I got the laugh on that. What a surprise. In that context, I just want to say why I had such concerns about coming here today. So I'd like to, for 1 minute, to just explain it. Our post-Enlightenment world, which is the world in which women, people of the LGBTQI plus community, and people of color thrive, is based on the idea that we deeply respect people even when we fundamentally and grievously disagree with what they say. And I'd like to use as a thought and experiment a completely different and very sensitive political issue that is one that touches me personally. There are people who think that I have committed murder and a sin because I've had an abortion. Obviously, when people have these opinions and express them, I find that deeply distressing and hurtful. But nonetheless, it would be wrong of me to label people who have that opinion as hateful. They are genuinely held beliefs. And those who advocate peacefully for laws and medical practices to reflect that belief are not hateful. Similarly, there are some like Helen Joyce who believe that being a woman should be defined by biology instead of gender identity, and advocate for laws and medical practice to reflect that. Regardless of our beliefs, it is wrong to label these opinions as hateful. Free speech advocates were correct to be outraged by Professors Rogerson's and Spencer's attempt to use their public position to shame those who wanted to listen to that particular side of the debate. Thanks for letting me express my concern. I realize this is not necessarily where these views should be expressed, but I also don't think Twitter is a place these should be expressed, and I don't think email is a place these should be expressed. I think these views need to be debated in fellowship. Thank you for your patience. In return for that, I've brought some gift copies of Trans, for Consequentiation, and I have brought some brown paper bags for you to put them in. Feel free to come up at the end. And now to something completely different. Thank you. So what I'm interested in is early blind individuals. And I'm interested in early blind individuals because humans are incredibly sighted animals, right? If we put earplugs in and headphones in, we're still perfectly able to make our way around the world. But put us in a pitch dark room and most of us are lost and helpless. We're blind. And yet blind people adapt to this amazing challenge with incredible abilities and skills. And it's a really impressive example of diversity in action. And what I'm interested in my research is how we have these children that are so diverse and have such different experiences from us, and how do their brains allow them to not only have a different experience of the world, but thrive within that experience. And so this is going to be a talk about one particular aspect of that, which are two regions of the brain, the planum temporale, which is a region in auditory cortex that we think is closely associated with understanding auditory motion in the world, and a region HMT+, which we think is closely related to visual motion processing in this world. And what I'm interested in this talk is talking about how changes in the responses of these two areas are associated with behavioral abilities to understand the world in a way that a sighted individual cannot. And I'm going to talk about these two specific examples later. Okay, so I'm going to start by talking about the brain, and then I'm going to start talking about behavior. It's pretty straightforward. So when we do a task, there's an oversupply of oxygenated blood to activated regions of the brain. And deoxygenated blood and oxygenated blood have different magnetic properties. And so, with a little bit of superconductivity and a dash of quantum mechanics, which is a very sexy way of saying fMRI, we can measure these magnetic signals in the living human brain. Okay. And this is kind of an example of a classic experiment where what I'm presenting is a set of moving dots versus stationary dots, moving dots versus stationary dots, and regions in the back of the head, which are responsible for kind of visual processing, are showing, this is sped up by about a factor of 10, are showing activity, and I'm showing these activity as a statistical map. And there's a region kind of on either side here, called HMT+, that is active. And this region we know from many, many studies, and because is unresponsive for visual motion. The back of the head here is responding to that visual motion, but it also responds to a bunch of other things. That's V1. It had long been suggested that this, so the question is like, okay, if you're someone who's blind from birth, would visual MT respond to visual motion? Or would it not? Is this experience, is it innate? And secondly, given that this person has no or very little experience of visual motion, would it respond to auditory motion instead? And that's this idea of metamodality, that the region maybe isn't so much tied to an idea of visual motion. Maybe it could just do motion, and it could do it in any modality if vision isn't available. That was the kind of idea that was out there at the time. And so a postdoc of mine, Melissa Saenz, decided to look at this. Now, the issue with MT is it's in slightly different places in every different individual, so you can't look at a blind person and say, oh, that's where your MT is. So how do you get around that? She took two sets of very rare subjects. They're sight recovery subjects. One was congenitally blind, the other became blind at 3.5. Both of them were blind for almost all their lives. They got their sight back around the age of 40 due to various reasons. And so the idea is that, okay, in these blind individuals who get their sight back, we already knew that they could see visual motion. So now what we can do is we can look at the regions of the brain that respond to visual motion, we can look at the regions of the brain that respond to auditory motion, and we can kind of see what happens. So this is the visual motion localizer. It's very similar to what I showed you before. Moving dots, stationary dots, moving dots. Super simple. The auditory stimulus is this kind of, it's a sound going from left to right. It's using either auditory level differences, so louder in the right loudness, or phase differences, so basically the difference in timing onset between the two ears. And we actually had moving, stationary, and silent in that case. And the silent subjects closed their eyes for that bit. So in sighted subjects, what you have here is I've shown regions in yellow, with regions that are responding to the auditory motion. I'm showing in blue the regions that responded to the visual motion, and I'm showing in green the regions that responded both to that visual motion stimulus and to that auditory motion stimulus. And what you can see is in the sighted subjects, there's almost no overlap. And what overlap there is probably us not being very good at unfolding. We didn't know Zoe. She's much better at it. And so what you see is there's this region here in blue, which is the MT. Is there a pointer by any chance? Or I might just want to wave my arms around. Oh, brilliant. Thank you.
Yes.
All right, he's still speaking to me. That's good. If my body is found later, just looking at you, John. Here's the area MT. Here's this area. There's an auditory region that's just kind of anterior. That was later identified by Olivier Collignon as auditory. He calls it auditory MT, but you can see that there's very little overlap between the two areas. So MT is not responding to auditory motion. Interestingly, and I think this is an important point for anybody who does fMRI, because MT's location varies and this auditory motion area varies, if you group average all these brains together, these areas will closely overlap. And it will look like this area is responding to both. It's just not doing it in the individual anatomies, and that's a really important point. And group average data, when you see overlap in group average data, be very suspicious. Here are sight recovery subjects, and you see a completely different pattern. Here you have the region responding to auditory motion, and it's almost completely overlapping with the region that responds to visual motion in the subject. So it looks like this area MT that responds to visual motion, it's still there in these patients, even though some of them had not had vision until adulthood. But this region is also responding very strongly to auditory motion as well, which is really cool. Just the last thing we did was to check that this really was auditory motion it was responding to and not something else. So this is auditory motion described by interaural time differences and level differences, and you see a response. It doesn't respond to a volume change. It doesn't respond to an FM sweep. And it doesn't respond to speech versus backward speech. I won't try to imitate that. That would just sound crazy. So the next question is, okay, we see responses to auditory motion, but is this just a kind of artifactual response, or can we tie it a little bit more closely to the perception of auditory motion, to what blind individuals are doing in the world? And so this experiment was inspired by driving into school, university, and I saw this blind woman. This is not her, but it's exactly the same intersection as I saw. And you just think it's a blind woman crossing the road, and then you realize something really interesting is going on, which is that the cars coming this way are obviously going to stop. Well, we hope they're going to stop, right? But the cars behind here, they can't see her cane, right? So they're not going to stop. And so she's going to have to tell the difference between sounds in front of her and sounds behind her. And as you all know from Sensation and Perception 101, I don't know what the British equivalent is, but like, it's very difficult. This is a really difficult task with your eyes closed. So she's actually performing a really difficult task where she's having to segregate motion sound sources. And so we decided to try to design a task that kind of replicated this. So what we have here is 6 what I call cars. People who are in auditory acoustics hate this description, but it works. So each of these cars has a different frequency band. So they're kind of white noise in the auditory domain, but some of them are like trucks, they're like shh, and some of them are like little electric vehicles, and they're like shh. Okay, so they all have a different frequency band, and some of them are traveling from left to the right, and some of them are traveling from right to left, and they all start and stop at different times. Kind of, they go around in circles, but kind of as they flip back to the other side, they disappear. That sounds really weird, but it'll have to do. And we have 12 1-second sweeps. And we have conditions where they're 100% going one way, and everybody can do that fine. There are conditions where 50 are going one way and 50 are going the other way, and people are guessing. And we have a condition where 6 are going one way and 2 are going the other way. And that condition is actually really hard. This is kind of what it sounds like if you don't have fancy speakers. Stop. Thank you. All right. So what you see is that sighted subjects do about 70% on that task. They can do it, but it's hard. Blind subjects find it much, much easier. They're much better at this task. So that's good. That means we're tapping into the kind of mechanisms we're interested in, the things that are making blind people really good at navigating an auditory world. So the next thing we did is we took that task and we did it in the scanner, and we simply asked participants in the scanner on these trials, is the sound going to the left or is the sound going to the right, okay? And we take the trials in which they're correct, and we use that as a training data. So here we are looking at MT. It doesn't matter whether we look at right MT or left MT, the result's the same. And imagine if we take this MT and we have a bunch of vertices or voxels. It doesn't really matter what space you use it in. And here's a bunch of voxels. And this is the average response of each one of these voxels when the sound is going to the right. And this is the pattern of responses in these voxels when the sound is going to the left. And even though the mean response to rightward sounds and leftward sound is identical, this pattern of response within individual voxels just differs a tiny bit between going leftward and going rightward. And so those are our training data. So that's like 9/10 of our data. And then we take the 10th set of data, and we basically have a machine algorithm decide, does this look more like this pattern, or does it look more like that pattern? And if the machine algorithm says, oh, I think it looks more like that, then we guess that the sound is going to the left. And if we say it looks more like that, we say it's going to the right. And then we count how often the machine algorithm gets this right. In fact, we used the simple linear discriminant. We didn't do anything fancy. And if we get it right more often than chance, what that means is that this region of the brain carries information about the direction of the sound. So we did this both with the 6 out of 8 car stimulus, and we also did it for the forward in each direction stimulus, where it's really just the percept of the person. that we're decoding. There's no right answer, 4 going this way, 4 going that way. So there's no right answer. So we're just saying, what did they say? Can we decode from these brain responses what the percept was? Okay, so we can link this kind of more tightly to the percept. So what you see is remember, this is an auditory motion stimulus. In the sighted subjects, you cannot decode the direction of auditory motion in MT, which fits with what I've already showed you earlier, that you don't get an auditory response in MT. Early blind, you can do it. Its percent corrects are fairly low, but that's pretty standard for MVPA. Again, you're kind of neurons for too boring. I'll explain it later if you. Okay. Whoa, come back. If we look at late blind individuals, so people who had normal sight up till about 30 or 40 or 50 and then lose their vision, they've been blind for at least 10 years in our sample, they're at chance again, and this is a sight recovery subject, and he's really good in the scanners. He's got a high percent correct. So what that's showing is that this ability for MT to be taken over by auditory motion is clearly a developmental phenomenon. You don't have it if you become blind late in life. And it isn't blocked if you get sight back. So it's something that happens in early childhood. Here's what I think is the most interesting result of this talk. The postdoc kind of went silent for a while, right? You know how postdocs do. They kind of like, and finally I go, and I'm like, what's going on? She's like, I can't go to platinum temporale. Oh, okay. Have a snack. Calm down. It's okay. Can't go anymore. And so what happened is now she's trying to decode the direction of auditory direction of motion in this area of planum temporale that is an auditory motion area. She can do it fine in the sighted subjects, which is a replication of a previous study. So planum temporale can tell you whether the stimulus is going to the right or left. Couldn't do it at all in early blind. Really couldn't. That, again, is a developmental phenomenon. So in the case of late blind subjects, they're like sighted subjects. We can decode in planum temporale. We just can't do it in the early blind subjects. Now, we didn't make a big deal out of this because it seemed so weird. But this actually later got replicated by Olivier Collignon. So this, despite being really weird, is really, at least been replicated. I don't know if it's true, but it's replicable. It's a start. And when you think about it, it's really interesting. Because remember, right planum temporale hasn't lost any input. It's still getting auditory input. Auditory input isn't disrupted in blind individuals. So the only reason for right planum temporale to have lost its ability to do auditory motion is because MT has somehow stolen it. Right? It means that there's competition between cortical areas for functional role. And these aren't even neighboring cortical areas. They're quite far apart. And so that is really fascinating and weird. We know that, and now the question you're all going to ask is, so what does planum temporale do? And my answer is, I don't know. It does audition. It doesn't do motion. And it's really hard to work out what an area does when you have no idea how to start. How are we doing for time? I'm going to make a brief digression here. So one of the other things, so this is work done by Libby Huber. So what she said was, okay, if MT is doing auditory motion, then what we presume blind individuals are using MT for is tracking objects in space, right? But MT isn't just tuned for motion. It's tuned for spatial frequency, it's tuned for disparity, it's tuned for kind of other features of objects which allow us to track, multiple moving objects in space. And so if MT is really tracking moving objects in space, it should be tuned for frequency as well, right? Because frequency is a really good cue for an auditory object, right? If I'm hearing John Mullen running this way, he's going, and I hear a bird going that way, it's going, right? And I'm going to use my frequency cues to separate those two objects. So she ran this kind of very pretty example where we have these noise bands that are kind of like, so they've got these frequency. I can't go really high with a noise band. But they kind of vary in frequency over time. And what we do is we basically fit a tuning function on the cortical surface that says, okay, what frequency of moving stimulus does this region of cortex respond to? Now, this is what I've done to kind of show this in more detail. This is a picture of a brain. This is a kind of section where MT is. Here's the responses to moving versus stationary dots in site recovery subject 1 and site recovery subject 2, and this is how she drew her ROA. She decided that that belonged in there. So now we're going to say, well, okay, what happens to frequency tuning in this area? And what you can see is we have to decide kind of what's significant. That was really complicated. This is a pretty stringent definition. In Mike May, most MMT showed frequency tuning. In SR2, only a few subject voxels showed frequency tuning. And this was set at a stringency threshold where for sighted controls, nothing passed threshold. And so what you can see is that there's regions of MT that are responding to different frequencies, but there's no kind of map. We spent a lot of time kind of trying to quantify the fact there is no map, but basically there's no map. So it looks like there's kind of tuning for frequency, but it's kind of scattered within MT, and possibly not that strong. Okay, so to kind of sum up where we are so far, what we see in blind individuals is really interesting modifications in the brain. We see that this area MT starts responding to visual auditory motion in individuals who are born early blind, and we see that planum temporale seems to lose that ability to respond to an auditory motion. Look at that, it's like a stimulus. So now what we want to say is, okay, having done that, what is the impact of this on behavior? Like, how does this help blind people make their way around the world? And what we're going to start focusing on a task that's a little bit more like this task here. So in this task here, this is, there's various names for it. Noisy Bowl is one of them, but I can't. This is a different game. But anyway, you get the point. These are blind individuals playing. They're blindfolded because blind people have different levels of vision, so this puts them all on an equal playing field, right? You don't want someone who's just got low vision playing against someone who's fully blind. So now they're all fully blind. This bowl kind of jingles. But what you can see is that they're not just sort of chasing the ball, right? They're also, he's blocking this other player, right? So they're keeping track of multiple moving objects. They're not just keeping track of the ball and chasing the ball like a kindergartner plays soccer. They're playing soccer like soccer players play soccer. They're blocking and they're thinking about strategy and the other players in the game. Okay. So I'm going to take a step back and talk a little bit about kind of motion. So, okay, motion is the movement of objects through space over time. And you can kind of draw a moving object, like a ball, going, through space, in terms of where it is in X and Y over time. So if you have, for example, you have a bar that is moving in a certain direction, you can actually kind of reduce this diagram into an XT diagram. So this is a vertical bar, because we've collapsed over Y. So it's a vertical bar going from left to right. Okay, so what we've done is we've said we don't care about the Y direction, we're interested in where this object is in space X over time. Okay? Now there are various ways that the visual system could represent that bar moving in space and time. And one of the simplest is something called a separable filter. So this is a separable filter that's basically made by creating a Gaussian or something like that, and multiplying it in the time direction and the space direction. Okay? And so the idea is any point here can be defined by the multiplication of these two separable functions. That's why it's called a separable filter. And when you look at the response to this separable filter to various kinds of stimuli, like a bar moving from left to right, it responds to that. It responds less well if the bar is moving less far over space and time, so that's a faster bar. It responds very well to boop, boop, right? And then it's inhibited by things that are moving in the wrong direction. Okay, so that's called a separable filter. And this may be familiar to many of you, but, revision is always good. This is what's called a non-separable filter, because I cannot describe each point in it as a function of two, dot product of two functions. It's like an oriented bar. And what you can see is this responds about equally well to a bar going across as it does to 2 points. It's inhibited by these other things. So one point to be made is a separable filter will respond to a smoothly moving object, as well as a boop, boop, kind of stimulus. And the same is true for a non-separable object. They will respond pretty well to a moving bar as well as to but they're very different kinds of filters, right? So these are very different neural mechanisms, even if the differences between them are fairly subtle in terms of neural response. Now, we know that MT has non-separable tuning. We know it has these oriented filters. We know this from a ton of work in macaques. And I'm going to describe here a psychophysics experiment that shows the same thing. But we basically kind of know this from a bunch of recordings of macaques. So in this case, this is Peter Neri. He has this very elegant experiment. So there's a bar. It's either going like this, or it's going like that. And on top of that, there's noise. And the noise is basically that each of these strips over here are changing contrast over time in a kind of random way. So it's kind of like, it's like white noise, but it's one-dimensional, right? The X direction has been thrown away. And then what he does is he says, okay, I'm going to add together all the, and this stimulus, bar stimulus is very low contrast. It's kept at about 65% correct. Okay? So this bar, so a lot of the time they're going to get this wrong. And obviously the times they're going to get it wrong, if it's, let's say the bar is going down, actually this bar is going up. Let's say the times they're going to get it, let's say the bar is going down, the times they're going to get it wrong, and say it's going up, is when at the beginning of the trial these things are right, and at the end of the trial these things are right, right? Because then the noise is going to look like a stimulus. Does that make sense? Yes? Everyone's heads, one way or another. So you're basically saying, okay, over time I'm going to look at the characteristics of the noise, I'm going to throw away my signal, I'm just going to add up all the trials where the stimulus was, where they got it, all the trials where they said it was going up, and I'm going to add together all the trials where they got it down, and then I'm going to make a filter of what they were looking at in this, basically, in this space-time grid. So here's space, and here's time. So now this is space. Along the y direction, this is time. And what you can see is that people are performing this task using an oriented filter. So if they're kind of having to decide, if noise, and this bar here would, let's say, be a bar there, it, haven't explained this very well, but basically that from the noise you can construct a filter of what the person is paying attention to when they do the task. So Wen Zhu basically took this task and just moved it straight to the auditory domain, which was really good because actually the vertical domain in audition is a mess. So just keeping it on the horizontal made life easier. So here what you have is space and time, and you've got an auditory stimulus that is going, in this case, from right to left. Not sure. My rights and lefts aren't good at that's the time. And what we thought is, well, okay, in early blind individuals, we have these responses in MT. Maybe we'll get separable filters in blind individuals, and that would be non-separable filters in blind individuals. Maybe moving to MT will mean that these blind individuals start using non-separable filters, and that would be so cool. And the answer is, no, it isn't that cool. So here's our cited subjects, and what you can see is they've got separable filters, and here are early blind subjects. You can see they do it different, but they still have separable filters, right? So what they're doing is they're listening for sound onset, and they're listening for the sound offset, and they don't really care what the sound is doing in the middle. They're not paying much attention to that at all, okay? And we quantified that with a really simple model. We basically created one model that basically consists of kind of something that's similar to two Gaussians, another model, another kind of filter that looks like this, and if you set this parameter, where's the equation? A plus AI2, if you set A as 0, that's a separable filter. If you set A as 1, it's a non-separable filter. And what you can see is both of these are really showing separable filters. And that's simply quantifying what you can see with your two eyes. In the old days, back in the old days, we wouldn't even bother, but nowadays, people like statistics. So then it's like, okay, that's weird, right? We have this move. Okay, we know in blind subjects the right planum temporale isn't responding to motion. We know that MT is, so we think that it's move. We know that MT has non-separable filters, these diagonal filters. We know they exist in primate monkeys as soon as you can measure them. Tony Movsham has collected that data, he just hasn't published it yet. Surprise. Right, so why then aren't blind individuals using separable filters, right? It's right there, it's right there in MT, why can't they use it? And so Wuju did an ideal, this was really clever of her, she did an ideal observer model. So she basically sort of said, okay, if you have a machine learning algorithm that can use either separable or non-separable filters, and she has a whole series of filters ranging from, this is a non-separable filter, which is kind of centered on kind of where the stimulus is, and here's a really narrow non-separable filter, and here's a really broad non-separable filter, and you have this task that we had, so this is a sweep of noise, sound going among this noise going to miss. What's the predicted threshold? So basically we're saying, okay, if you make a computer do this task with these different kinds of filters, how does it do? And what you can see is the best performance here is if you have a really narrow filter that is separable. But this non-separable filter is really close, okay? It's really close, and in fact, it's as good except at the very lowest levels of internal noise. So this is kind of how much internal noise as opposed to this external noise you have here. And when you think about auditory motion signals, you're having to construct that perception of motion from ILDQs, ITDQs, etc. This is a very noisy signal. And it's very likely that, and we know that our ability to do auditory spatial localization is actually pretty weak. So it's very likely that we don't have filters like this for audition, because why would you have filters that are really narrowly tuned for space when you can't do really narrowly tuned filter space, right? We can distinguish like 1 minute of arc visually. It's difficult to discriminate 1 degree in audition. So these filters don't exist. So given that these filters don't even exist probably in humans, it makes sense that these blind individuals are relying on separable filters. And that's really interesting. It implies that as MT is colonized for auditory motion, it's actually shifting the way it's solving the task to be optimal for blind individuals. Again, what we did find is that when you, as well as measuring how the noise is influencing how people are doing the task, you can also measure, you remember we kept people at 65%. You can say how much amplitude you need to be at 65%. And what we see here is blind individuals need far less sound for this traveling sound signal to be at 65% compared to sighted control subjects. So we know that blind subjects are better at the task, that they are still using separable filters, and they're still using separable filters. So how then are they better at the task? So if you look, here's our sighted again. This is a pattern of the filters they're using. This is the early blind. This is a pattern of the filters they're using. And this is the difference between them. And what you can see is that the difference between them isn't here. It's not like they've got a kind of diagonal pattern here. The difference is right here. And that's actually, remember the stimulus, actually the white noise comes on, and then the sweep comes on like a little bit later and goes across and ends a little bit earlier. And what's happening is that sighted subjects are just listening from the beginning of when the sound, the noise starts. And early blind individuals are kind of shifted a little bit towards when the actual signal starts, which was a little bit later. Does that make sense? And so if we measure, the other thing you have is the blind subjects. You can see here, this data is much cleaner, right? This is kind of noisier. This is averaged across 8 subjects who did the same number of trials. If you look at individual data, the sighted subjects look pretty noisy. The early blind subjects look beautiful. And that's kind of reflected here, where you can see that the amplitude of the Gaussian, best fitting Gaussian to match this data is much lower for the sighted than the blind subjects. You could think of this as the amplitude of the Gaussian. It's the equivalent of saying that the signal to noise is higher in the blind subject. And then what you can also see is there's a shift in the spatial center. If you fit a Gaussian to these, the spatial center shifted for the blind subjects, the center width, and the time center and the time width. There are differences across all of these things. And what these differences all kind of come down to is a really kind of simple idea, which is that there's a kind of, the stimulus, remember, starts kind of offset spatially and goes to here. This is kind of the onset of the spatial stimulus. And you can see that the blind subjects here, their peak of where they're paying attention to tends to be closer to this onset than for the sighted subjects. And it's the same thing with the time, especially the time. The peak, the blind subject knowing when to listen, whereas the sighted subject must less likely know when to listen. So what we're seeing is not some sort of major qualitative change in what's going on, but instead a little bit of a tuning where they're just getting much better at working out where the signal is inside this noise. Okay. And that's it. So, what have I shown you, or tried to show you? Visual area HMT is intimately involved in auditory motion processing in early blind individuals. It seems to be a developmental adaptation requiring blindness early in life. It seems to supplant the auditory motion area, right temporally, and that suggests something like competition between cortical areas for role is going on. There's actually, it's kind of new. It's kind of very surprising because there's not a whole lot suggesting that would happen in the literature. You know, we're very used to the idea of inputs competing for representation, but not for different areas competing. And finally, early blind individuals have enhanced auditory motion processing abilities, but the filters they have are still spatially temporally separable, and their ability to do this seems to reflect a kind of refinement of kind of tuning rather than a sort of shift in how sound is represented as a result of moving to HMT. All right, thanks very much.
Many thanks indeed, Ione. We have a little break now for those who need to get away, and then we have questions. So. Brian Moore.
Yeah. I think in all the experiments you described, the subjects themselves were stationary, but obviously auditory motion perception in everyday life occurs while you're moving around. So do you have any data where both the subjects move and there's movement in the scene? And does this area MT really what is it really responding to? Does it allow in any way for the motion of the listener?
Yeah, I think probably self-motion is, I'm trying to think. So, again, the auditory spatial processing is pretty weak. So the best example I can think of for blind individuals where they're using self-motion is when they use a cane, because experienced blind people with a cane will tap. You'll hear them really tapping because they're listening to the echoes, and they're listening. But I don't think, I haven't heard, like even, I can't think of an example where blind individuals use self-motion to get extra information about the world, like, you know, the way, you know, cats or something might do. You know, cats do this when they're thinking about jumping and that kind of thing.
But you mentioned like the difficulty of telling front from back, and we can resolve that with lateral head movement.
Actually, yeah, they do that. So when you're talking to a blind individual, they will often, because they don't have the same incentive to look at you, they'll often look away. And it's a slightly disquieting because it means they're concentrating because they're putting their best ear towards you. and kind of focusing the sound, and they're probably it's, but they'll actually look away, and so you're like, oh no, yeah, it's okay. You know, it's a different social signal. So, but again, I don't know if it's. I haven't seen them moving. I see that you'll see them. I don't know. We haven't done it. You can't do it in a scanner. Motion in the scanner is a bad thing. It's a really interesting question. I'll have to think about it. It would be nice to kind of talk to blind people and find a kind of task that has some sort of ecological meaningfulness.
So in the first part of your talk, you had the experiments about spatial auditory motion. I mean, this might be very naive, but what I understand that most of these interval and time differences cues are encoded in the brainstem. And so what exactly is HMT doing?
Mm-hmm.
And what are the computations involved? Are there any direct anatomical pathways that connect these two regions, or do you have any EMS experiments with which you can actually tease apart these effects?
Yeah, no, that's not a naive question at all. So yes, we think that the basic computation of the cues are probably done subcortically. There is a little bit of evidence. It's very difficult to do good neuroimaging subcortically. There's a little bit of evidence that there might be cross-modal plasticity within the superior colliculus. I wouldn't call it. It's Holly Bridge is the lead author on that. I'm an author on it. I don't think it's definitive. Shouldn't say that about my work. It's definitely definitive. But I think what it's more about. And again, basic motion computations happen in V1, right? We saw when I put that first stimulus up, V1 was lighting up. What I think, the reason, I actually don't think MT is necessarily doing the computations, even though I kind of hinted, that was kind of the way the talk was oriented. I think what happens is by taking over MT, what you essentially do is you take over the connections that MT has to all the other areas that allows you to have a map of the world that includes motion, right? MT is connected to, reaching, it's connected to motion moving through the world and so on and so forth. And so rather than try to recreate that, and most of what we do when we create this world that we move through it was designed for sighted individuals. So I think the way that in taking over MT for visual motion and auditory motion of blind individuals essentially allows you to co-opt that entire network and basically funnel and so now you've got that structure. And so I think it probably has less to do with the computational capacities of MT. And what's really interesting, is that maybe even though MT now has moved to the separable kind of model, the output to MT to other areas is probably still sort of a labeled line for continuous motion, because blind individuals don't report not hearing continuous motion. They report the reports of motion sound like you ask them, they talk about motion the same way auditory motion the same way we do. So it might well be that doing these computations in MT also allows you to get the kind of idea of continuous motion from MT that is really important. And I don't think we have a strong sense of continuous motion from auditory motion per se, because again, most things in the auditory world aren't continuous, right? We tend to kind of hear something here and then hear it there, a bird singing or someone walking. A lot of these sounds are very discontinuous.
Yeah.
I have a bit of a methodological question, which I think I know the answer to, but I just wanted to ask it. So you're doing this auditory task in an MRI scanner, right? And an MRI scanner is quite noisy. So I was just wondering, I can imagine that people that are early blind or that they have a much better developed they can distinguish very subtle sounds better.
Mm-hmm.
So I was wondering how, do you have perfectly noise cancelling earphones that you can, or headphones that you can then play stimulus through, or might also be that people that are early blind are way better at distinguishing very nuanced differences between the MRI scanner and your stimulus?
Yeah, so the answer is no, sadly. I think my vague recollection, I might be wrong, is Fang's experiment in the scanner might have been done using a sparse protocol. In fact, I think it was. So well, we ran it both ways. I can't remember what, the point is I can't remember what we ended up doing. So sparse protocol, what you do is you rely on the fact that the blood signal flow takes about 3 seconds to kind of peak. So what you do is you basically don't do an acquisition, so the scanner's silent. You play your sounds, and then you take your acquisition. So it's silent, you do your auditory stimulus, blah, 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 and then like that. Which again is, you know, it's not perfect. We tried it that way. We also did that. So that's one hack. It's really expensive because it takes a really long time. The other way is just doing it continuously, noise blocking, and assuming that because it is a constant signal, in that classification, when we have 6 out of 8, we only use the correct trials. So ideally, we're not doing. And again, if we had been able to do it in blind and not the sighted, I don't think that would have been a bit dubious. But what we see is this double dissociation where we can classify implanted temporal but not MT in the sighted, and vice versa in the blind. And that's why we don't think it's just that sighted people are losers. Right. It's really interesting. Normally when you work in a population that's neurotypical, you're always worried that the population that you're working with just can't do the task for some reason. In our case, our problem is that the sighted people just can't do the task for some reason, which is kind of awesome. We have trouble on piloting.
Tristan.
I have a bit of a silly question and maybe a question more about functional cross-decoding, but using maybe something like EEG or MEG. I'll start with the silly one. What's your intuition about the differences at the structural level for the early
Blind
will
individuals.
it be possible to DTI these people? And
Oh, everybody's done DTI on these people.
I know, but does it say something about your results that it's?
So when you just do a kind of general diffusion weighted things and you look for structural differences, you generally don't have enough participants. It's hard to get an N of bigger than 20 for blind individuals, and you just end up with non-applicable garbage. There seems to be a big difference in the connections between occipital lobe and parietal. That's something that gets consistently replicated, but that's it. And nobody knows what to make of it. Collignon has this really interesting finding that we're hoping to replicate, which is that there is a loss of connectivity if you look specifically at tract between MT and planum temporale. And what's interesting about that is it's the opposite of, I think, well, certainly the opposite of what we were expecting to find. I'm pretty sure it was the opposite of what he was expecting to find. We were hoping to see an increase in the link. Instead, you see a decrease. One possibility is that usually the information comes actually from MT to planum temporale. That the link isn't from planum temporale to MT, it's from MT to planum temporale. And so blind individuals, that link for some reason gets kind of, doesn't go anywhere for some reason. But we don't know. So again, his findings are, they're great, but they're weird, and it's one population group, so, and it's DTI, so, you know, I wouldn't get too excited before it's replicated.
And do you think it's possible to do a design to replicate these results using MEG or EEG? Because you already know in these 2 participants that are very interesting. I'm sure you can find a few more. I mean the normals, whether you can train with motion, the same, similar, but what you think is comparable in terms of cross-modal in the sense of modality, sensory modality, and also the cross-decoding.
Cross-decoding. So I think it would be difficult with even MEG to definitively, PT and MT aren't close together.
I'll rephrase. Forget about space.
Okay.
Functional, real, time decoders. It will
Okay.
be about the information,
Okay,
not
so-
about the space.
So what we haven't shown you, what I have not shown you, which drives me crazy, is I haven't shown that in the sight recovery subjects, I can predict the direction of auditory motion from a visual motion training set and vice versa. I'm sitting on that data right now. It's just, for various reasons, proved really difficult to kind of get that. Basically, COVID happened. It would be very interesting to see if we could do that in site recovery subjects using EEG, because again, you don't really care about the spatial location. We're at the moment, we're just trying to do this with fMRI. It would be interesting. At site recovery subjects are hard to find that. Like finding a few more, that's like, you know, you get them, but they're mostly in third world countries where children haven't had good ophthalmic care. So there are lots of site recovery people, and there are lots of MRI machines, but if you have a research grade MRI machine, luckily you have enough ophthalmic care that you don't have site recovery patients, and vice versa. So those two groups don't line up.
Hi. You sort of started speaking about this, but I'd like you to elaborate if possible. By which, in terms of the subcortex in the early blind subjects and sight recovery subjects, is the story analogous to the cortex? Is it a complete reorganization of function, or is it more hardwired?
It's really hard to get functional responses, auditory functional responses in the subcortex, and we have not had a good enough scanner to do that until really recently. So Holly Bridge has done some beautiful work on this, kind of in collaboration with us at Oxford, with anophthalmic subjects. So these are individuals who never even have retinal waves, so they're kind of fascinating. What we know is that, and again, it's very difficult to kind of be able to tell the difference between inferior colliculus and superior colliculus kind of anatomically, kind of in the images, and the MGN and the LGN. So we have some indication of reorganization in the superior colliculus. We haven't really got, we don't know if it's top down, and we don't know what kind of selectivity it has, whether it's just anything auditory or we just really don't know.
And thalamically? Thalamically, perhaps slightly easier to look at?
Yeah, so the MGN, again, it's
They're small.
they're small and they're difficult to identify in using a T1. I tried to get a postdoc to identify using proton density imaging, and basically she started having mental health difficulties, so I took her off the project. So it's not easy. Because of that, yeah. Because of that, yeah. Are you doing that proton density imaging? Yeah, no, it was totally reasonable, right? I was on her side on this, but like it was really like, okay, this project has to stop now. You know, you've been spending way too much time staring at two tiny little bumps on the screen. It's not going on.
Right.
All of the motion that you used was simulated auditory motion, but not including cues that you might normally get from the pinner or from room reflections. So do you think that could be important? I mean, I assume your subjects heard everything inside the head, they just heard stuff moving inside the head, not in the outside world. And does that matter, do you think?
So I think for the one with the cars, actually we include Doppler, but we do not have a pinna shadow. The answer is yes, I do think it's important. Yeah, so the car one, we actually included Doppler, which is a great cue. So what we did is we did the physics and simulated the physics of a Doppler cue. We did not include, you can do a kind of basic pinna, you kind of take the average ears, but we haven't done that yet. We have that now in the code, and I think if we did that again, we would do it. But so we had the Doppler, so it did sound, it was out of your head. So we use this. I think now when we're doing these kinds of tasks, we're making it as realistic as possible. What we're not doing is doing recordings using in-ear headphones, which is the best way to do it, but it's really time consuming.
I promised Ione a gin and tonic before she gets her train back to York. She can't stay very long. But if anyone would like to join us there, I guess we'll be in all bar one by 5:45. And it's my obligation to buy anyone who's attended the Zangor Club a drink. So anyone who'd like to continue talking to Ione. She has 2 copies of Trans to give away because I am putting my hand up.
Would you like the paperback as well?
No, I'm not ashamed. I may not walk into my college with one. So I'd like to end by thanking Ione once again very sincerely for coming and telling us about this interesting and counterintuitive results. Thank you very much.
The thing I always tell students is if you get results that's completely not what you expect, you learn more than you would have otherwise.
You can still.
So first of all, I've got 2 of those already. So, well, I bought one for my wife, and I've spoken to you for her. So anyway,
There you go.
we
Good.
win. Yeah. So this is a question based probably on a lack of memory and all the details of what you said. So slight recovery patients show you can decode auditory motion with MT, and you can't decode auditory motion with
Temporarily. That's true for early blind as well.
Yeah.
I think not
Do
even
they-
for the previous responses for the previous ones as well.
I don't want to have to carry
But
that
it's
back.
true.
Do you want
I
that?
did that myself. You
There you
get
go.
like 5 responses in a row, and you
Can you
think on the next
decode
one, I
visual
think it's
motion
might be
in
that
your
this
slight
is
recovery
getting-
patients?
Yeah. The more troubles that you add, the
It's doing auditory motion. I
Yeah.
realise there are different bits of it.
yeah.
I know this is a very long question, a long answer.
Which they may well do, but I'm just wondering.
We don't know,
Explain
because
something in terms of frequency
my student has collected the data. He cannot.
Yes.
Maybe there's
No,
short-term
we can't do it.
adaptation in frequency shift detection.
He can't do one of the 2, and I'm reanalyzing the data right now to try to work out why not. So give me a week.
All right. So here's my follow-up question.
In the model as
So
well.
do these 2 patients show greater behavioural interference between auditory and visual motion if they're decoded in the
Yes.
same area?
Yes, that is really cool. We just have that data, it's beautiful. So what we have is, basically they have to do a direction motion judgment, and we have an auditory stimulus that's a distractor.
Yeah.
I agree.
And yeah, they get shifted like crazy.
Okay. Right. So given my success with that stupid question, and I'll see the stupider one. So what I liked was that for the decoding auditory motion and MT, including but for the basic finding of decoding of visual motion, I saw that experiment. I would have thought that the better control wouldn't be something too stationary, but something which is flashing. Because when something's moving, you're getting lots of on-site responses in the visual array.
Yeah.
And when something's stationary, you don't. So 2 things happening. 2 things are happening. It's moving and you're getting on and off response. So if you have a stationary flashing stimulus, does MT respond to that?
Actually, not as much. In fact, I showed that because it's what Melissa used.
Yeah.
Nowadays, we have limited lifetime dots that don't move in a limited lifetime. So the moving ones move in a limited lifetime, and the other ones flash on and off.
So it's part of the same array.
So when we're defining MTs, when we're deciding what MT is, nowadays we do exactly what you do.
Okay.
So they're dots. Well, we don't do that because that just produces this massive signal. What we have is we have moving dots, and the dots are individually coming on and off.
Oh, I see.
Right, so they're not all flashing on and off at once.
Right.
But
They're twinkling.
Each of them lasts about 10
Yeah.
frames.
They're a twinkling thing.
Twinkling, yeah. And that's what we use now for MT, because when you do that, you don't get, remember how I showed you, I showed the circles and said, ignore the stuff at the back.
Yeah.
That's how you get rid of the stuff at the back.
So my name's Bob Carlyle. I'm an auditory researcher.
Oh, great.
I mostly work nowadays. So I did my PhD with Brian Moore.
Oh, Yes.
But you know, somebody would require more us to quite hold them very. And what I mostly work with, so most of the first half of my career I did normal hearing work. I actually, as an aside, did a study with, for a TV programme with my colleague Audrey Cusack at the time, my postdoc, with the captain of the British blind football team.
Oh.
And what we did was there's a visual search task where you kind of track some objects moving around, and that was done. And that, let me get this right. So what we found, because it was a while back and it was mostly wondering. So so there's an area I think of the parietal lobe, which was involved in this visual search task. And we had two subjects. One was the captain of the blind British football team, and the other was a child producer. And so it's a really that was for TV, made for TV. It was pretty interesting because what we found was we had an auditory task. We use HRTFs as related to